Okay, so we are going to continue our study of boundary value problems. That is a PDE defined on a finite interval. Just as an example, I'm going to give a very familiar one, or one that at this point should be very familiar. The t derivative of u is equal to the double x derivative of u. And we'll give it some Dirichlet boundary conditions. So u of 0t equals u of 1t. These are both equal to 0. And then some initial condition, or u of x 0, is equal to f of x. The boundary conditions here, the Dirichlet boundary conditions, correspond, for example, if this is modeling the temperature in a rod, if u is a temperature in a rod, then having these 0 boundary conditions says that, according to some temperature scale, we're keeping the boundaries at 0 degrees. Okay, so what we want to do now is we want to take everything that we've done with separation of variables and try to put this in a way where we can make it a little more abstract to handle more, different problems than just this one. So what we're going to do is the following. You remember from separation of variables that we get two different differential equations. One in the t variable, which we could solve, and there wasn't really anything more to that than just solving it. But then for the x variable, we also had these boundary conditions. Then we got these things called eigenfunctions and eigenvalues and things like that. And so we want to focus on that. So motivated by the fact that the x operator, so I have a sort of an operator in t, a differentiation in t, and then my x stuff, which is what goes along with the boundary conditions, that is what's going to give me the eigenvalues and eigenvectors. Motivated by that, I'm going to define an operator that just acts on functions of x. And in this case, L phi is going to be equal to phi double prime. Okay, so I want to study this operator, and I don't want to just have this act on any function. I first want to restrict it to the case where it's differentiable or twice continuously differentiable. But I also want to restrict the domain of this operator to the sets of functions where phi of 0 is equal to phi of 1, and that's equal to 0. Okay, so all we've done so far is just change our perspective a little bit from what we've seen so far. And I want to study the corresponding eigenvalue problem, which is L phi is equal to minus lambda phi. Now, if I had just done this at the very beginning of this chapter on separation of variables, it would be a little unclear why I care about this. But think back how we do separation of variables. These are the exact type of equations that come up when we do separation of variables. I'm just giving you a different perspective on this method of separation of variables. So we want to study this equation with this in the boundary conditions, and we learned that there are going to be solutions. Phi k of x equals sine k pi x, and then we have these eigenvalues. Lambda k is equal to k pi squared for k equals 1, 2, so on and so forth. Okay, now if you haven't done the other separation of variables stuff, if you hadn't done that first, this might seem like a little unmotivated in what I'm doing. But we remember, you should at least, even if you're not sure where this is headed, you should at least remember this from separation of variables. So I'm going to record this data down here. So I'm going to say if I define this operator, L phi is equal to phi double prime, and I have these boundary conditions, phi of 0 equals phi of 1. They're both equal to 0. Then I'm going to get these eigenfunctions that satisfy L phi k is equal to minus lambda k phi k. And I want to keep things a little abstract and generic for now. So I want to think of it in terms of this relationship here, but I'll just put, for the sake of definiteness, phi k of x is equal to sine k pi x, and I'm running out of room here. Sorry, lambda k is equal to k pi squared. Okay, so now what I need to do is I need to sort of connect this, which on the face of it might not have anything to do with that PDE. I need to connect this back to that problem there. Okay, so here's how I'm going to do that. In the older videos that I posted, and in the notes that I posted, I gave you a whole bunch of theorems regarding the convergence of Fourier series. And what I basically taught is that any function, as long as that function is continuously differentiable, any function, sorry, if you see me smiling, it's because my sweet mate just said hello to me, gave me a good morning gesture. Okay, if you have any function in the x variable that is piecewise continuously differentiable, you can expand it as a sine or cosine series. So we can expand it in terms of these eigenfunctions here. So what I want to do is I want to say, okay, for every fixed value of t, if I look at u of xt, if I make the assumption that the solution to this equation is twice continuously differentiable, actually, if I make the assumption that its second derivative, its second x derivative is piecewise continuously differentiable, then I can, for every fixed t, then I can expand u of xt as a power series in sine and or cosine. But since I have sine functions here, I'm going to use it sine functions. So in other words, what I'm saying is, for every fixed t, u of xt is a function to which I can apply the sine and cosine Fourier series expansion theorems. In other words, for fixed t, I can write this as the sum k equals 1 to infinity. Okay, I'm going to have my phi k of x, which is sine k pi x, but like I said, I want to keep it a little generic and abstract for now. And then I'm going to multiply it by a coefficient. But since the function changes for t, for every t I get a new function, really bk of t is a function, bk is a function of t. Because for every t, I'm going to get a different sine or cosine expansion. In this case, sine expansion. And this is the method called eigenfunction expansion. These vk's are called eigenfunctions, the lambda k's are called eigenvalues, and what we're doing is we are expanding our function in an eigenfunction, we're expanding our solution, u, to this differential equation in an eigenfunction expansion. And the operator L, like when we say eigenfunction, it's relative to this operator L, and the reason we defined L to be what it is based on the right-hand side of this equation. We'll look at more complicated right-hand sides this week as well. Okay, so now what I want to do is I want to determine what these bk of t's are. So here's how I'm going to do that. We know what it is. Like we've already done this. This is this method of eigenfunction expansion is sort of a different look on the method, a different perspective on the method of separation of variables. So we know what the answer is going to be here, which is why I started here. All right, so I'm going to take this, I'm going to plug it into the differential equation. So I know that the t derivative of u, and you can watch the videos that are going to justify all of this term-by-term differentiation we're about to do. If I do the t derivative of u, it's the sum k equals 1 to infinity bk prime of t phi k of x. Now notice this. I want to do the second derivative and set those two things equal to each other. When I do the second derivative of this function, when I do the second derivative is going to come in and just hit the phi k function. But that's just the same as doing this operator. Okay, that's very important. So I want to say that one more time. When I do the second derivative, if I term by term differentiate, which again, we're allowed to do based on the Fourier series theorems that we talked about. When I come up here and do the second x derivative, if I do term by term differentiation, the second x derivative is only going to hit the phi k's, but that's exactly, the second x derivative is exactly what this L operator is defined as, which is why we defined it to be that way. So now this is going to be equal to the sum k equals 1 to infinity bk of t times L phi k of x. Okay, because I don't want to rewrite this, and I want to, well, actually, maybe I will just rewrite it. So L phi k of x is equal to minus lambda k phi k. So let me just write this. I'm going to write this and then step out of the way. So we've got this sum, k equals 1 to infinity with a minus sign because it's minus lambda k. And then we've got bk of t, lambda k, phi k of x. Okay. So what we have, the t derivative of u is equal to this, and the x derivative of u is equal to that. So now what I'm going to do, because I want to easily compare these two things, sorry, I keep dropping my eraser. Okay, L phi k is equal to minus lambda k phi k, so I'm going to just make that replacement now. So it's going to be minus and lambda k phi k, that's what I want to concentrate on now. Now the phi k's, they're sine k pi x. So the sine functions are orthogonal to each other, so therefore they're linearly independent. So if these two things are equal to each other, they're both expansions. This is an expansion in phi k's, this is an expansion in phi k's. What this means is, let me just move the minus sign in there. What it means is that if u satisfies the PDE, then these two things are equal to each other. That's what it means for you to satisfy the PDE. That's what it means for you to satisfy the PDE. The t derivative of u is equal to the double x derivative of u. If this is the case, and they're both written in terms of the phi k functions, which are linearly independent, it means the corresponding coefficients are also equal to each other. So in other words, this gives me equation for the bk's. It says bk prime is equal to minus lambda k bk. In other words, bk of t is equal to bk of 0 times e to the minus lambda k t. So now I'm going to come up here and record this information that I have here. bk of t is equal to bk of 0 times e to the minus lambda k t times phi k of x. And again, I want to keep things generic at this point. All right, well, the next thing that I need to do is figure out what bk of 0 is. So bk of 0 corresponds to t being equal to 0. So I'm going to erase this now. So I need some other piece of data to tell me what bk of 0 is. So bk of 0 is the following. Or how can I figure that out? It's going to be the initial conditions here. So u of x0, well, I know on the one hand it's equal to f of x. And on the other hand, if I plug in t over here, I'm going to have the sum k equals 1 to infinity bk of 0 phi k of x. And so from everything that we've done so far, I know that bk, instead of writing bk of 0, because now in this context it's sort of taken away from the differential equation, so I'm just going to write bk is going to be equal to 2 times the integral from 0 to 1 f of y phi k of y dy. And I'm using y as my variable of integration because I'm using x up there, and in a minute you'll see what I'm about to do. Well, you'll see what I'm about to do. Okay, so we could say something like, how can we report our answer to this problem? There's multiple ways. We could say this is the solution to the PDE, where this right here gives me the formulas for the BKs. Of course, if you have f of x written explicitly in terms of signs, then you can just write out the BKs are going to be the coefficients on the sine function as well, so you could write it out that way. But there's different ways to report the answer. Here's what I want to do, because I want to sort of pave the way for stuff we're going to be doing next week when we look at non-homogeneous equations. What we can do is just take this integral and copy and paste it in there. This is one of the reasons that I wanted to write it with y variables instead of the x variables. So we're going to have k equals 1 to infinity 2 times the integral from 0 to 1 f of y, and I hope I'm not going to run out of room, phi k of y dy e to the minus lambda kt vk of x. And again, I'm just keeping things abstract like this with vk's and lambda k's, but also remember vk is equal to sine of k pi x, and lambda k is equal to k pi squared. Okay. And now what I'm going to do, without justifying this, but I can if I needed to, I'm going to interchange the role of summation and integration. And what we're going to get is 2 times the integral from 0 to 1 times f of y times the integral k equals 1 to infinity, and we're going to have e to the minus lambda kt vk of y vk of x dy. And finally, this sum right here, we can just call that k of xy, and this is going to be 2 times the integral from 0 to 1 f of y times k of x, y, t. I think I said k of xy, but it should be k of xy t dy. And now we're going to see that this is going to be related to something called Green's function for this differential equation. Okay, now again, I wrote everything very abstractly because I wanted to write it that way, because I wanted to pave the way for things that we're going to be doing, and I wanted to sort of encourage a more abstract viewpoint here so we can handle more difficult problems than this one here. But everything that we've done, like there's no new, this is the same solution that we got when we solved this using separation of variables the first time. The new thing here though is I'm explicitly using the fact that we can expand any function, quote, any function in terms of a sine series, and then we can term by term differentiate, and kind of going from that perspective. It's sort of starting, it's like the same thing, but in order to get to this perspective, we have to do the separation of variables stuff first, and now we're sort of starting with like the end result of that, in a sense, to do this method here. And this is going to be a better framework to work with to look at more complicated and more general problems.